Hi guys, welcome back. In this slice of physics, we're going to take a look at an example of figuring out magnetic field from a current in a long, straight current carrying wire. In order to figure out the magnetic field, we will have to determine its magnitude, for which we have an equation, and then we will use the first right-hand rule to figure out the direction. And as we do this, we will review our notations for vectors and current in and out of the screen or the page. All right, here's the problem we want to tackle. It says a long straight wire lies perpendicular to the plane of the screen at the origin. So let me start drawing as I'm reading. That's always a good practice when you're doing physics. Here's my x-axis, here's my y-axis, and so at the center here is the origin. And that's where the wire lies. And the wire lies perpendicular to the screen, so all we see is the cross-section of the wire as a circle. It's going in and coming out of the page at the origin. It gives us the radius of the wire, which is 1 millimeter, and it tells me that the current through the wire is 6.5 amps going into the screen. We know our notation. When a current is going into the screen, it's an X because we're seeing the back end of the arrow. So we're seeing the feather. So it's an X with a circle and closing that X to show the wire. So a circle with an X is current in. So I'm using the correct notation here to show the current. And I can write I equals 6.5 amps next to it, so I know how much it is. And it's asking for the magnetic field at 2 points. Point A is 3 centimeters to the right of the origin along the positive x-axis. So I'm going to use the color red to show that. So here's my point A. And point B is 5 centimeters below the origin. And I'm going to use purple to indicate that. So if that is 3, 5 is somewhere here. Okay, so this is B. All right, so we've captured all the information that's given in the question, and we are asked to find the magnetic field at these points A and B. First step, let's figure out the magnitude. So we're going to work with point A first, and then we'll go to point B. So I want to figure out the magnitude of the magnetic field at point A. So I'll call that BA, which would be mu naught times I. That's the current in the wire, over 2 pi RA. Remember, this R here is the distance from the wire to where we want to figure out the magnetic field. So in this case, RA would be this distance between where the wire is at the origin and point A. Okay, do not confuse this R in this equation to be the radius of the wire. R in physics more often is distance and very less frequently is it radius. So it's not the radius of the wire. So this radius of the wire information that was given in this question was purposely set there to confuse you. If you're just plugging and chugging and looking for a radius to plug into this R, you might use that, but that's irrelevant. In fact, most of these wires are very thin, and we don't care about the radius of the wire. The wire itself is thin and it lies at the origin. The radius of it is irrelevant. R here is the distance from the wire. So you can say from the center of the wire to the point A. All right, so the rest of this we know how to do. The mu naught is a constant that is 1.26 times 10 to the negative 6. The units of it are Tesla, meter over amperes. So let me actually write that over here. It's Tesla meter over amps times the current in the wire, which is 6.5 amps, divided by 2 pi, and the distance for point A is 3 centimeters, 0.03. And this R is just the distance, so I don't care about the sign of it. I just want the physical distance, which is always positive. But I want to convert it to meters so that the units will cancel and I'll get an answer in Tesla. So you can see that this amps here cancels this amp, This meter here cancels the meter here. So I end up with a unit of Tesla, which is the unit of magnetic field. And when you put this into a calculator and solve it, you will get 4.34 times 10 to the negative 5 Tesla. It turns out that 1 Tesla is a pretty big unit, so a lot of our magnetic fields will be in the order of a micro Tesla. All right, so that is the magnitude of the magnetic field at that point. And I'm just going to stay with magnitude for now and go ahead and calculate it for point B as well. So it's the same mu naught, same current in the same wire, so it's still I. I don't have to write IA and IB. It's the same I in both cases, but I do have to write RB because this is the distance of point B from the wire. It's not the radius of the wire. So once you put all this in, it's 1.26 times 10 to the negative 6. The current is still 6.5 amps. Divided by 2 pi, 0.05, converting it to meters. So then I'll get an answer in Tesla, and this ends up being 2.61 times 10 to the negative 6 Tesla. Sorry, negative 5 Tesla. And that makes sense. The value is smaller because I'm farther away from the wire, and because the distance is in the denominator, the farther I am, the weaker the magnetic field is going to be, which also makes sense. The wire is where the current is, so the farther you are from the current, the influence of it is going to be weaker. All right, so I've got my magnitudes. I'm not done yet because magnetic field is a vector, so I got to give its direction as well. So now let's go back to this picture and see what the direction will be. You have to use your first right-hand rule. So for direction, I use my first right-hand rule, where I make like a thumbs up kind of a gesture, and I rotate. I hope you're doing this. I'm doing this now, but you can't see my hand. Hopefully you're doing it for yourself. So hold up your hand in a thumbs up, loosen your fingers a little bit, and then turn and move your hand so that it's placed in the, like it's grabbing the wire with the thumb pointing in the direction of current. So when I do that, my thumb is pointing into the page right here. So I place my thumb over here and its thumb is pointing in. And when that happens, my fingers are wrapping around like this. So my fingers are curling like this, so that gives me the magnetic field direction. So the direction in this case is going to be clockwise around the wire. That's a correct answer if you are giving me a general sense of direction of the magnetic field around this wire, or if you're talking to me about magnetic field lines, they will be concentric circles that are going in the clockwise direction. But what we're being asked for is the magnetic field at specific points A and B. And at A, the magnetic field is not clockwise, it's at a single point. So at a single point, it's got to be a single vector. So the vector has to be a straight line. So how do we figure out the direction of the magnetic field at A and B from this knowledge that we have the direction as clockwise, in this case, around the wire with the current going into the page? Well, let me show that to you here. So if I have a current in a wire that's going into the page, when I use my first right-hand rule, I see that my magnetic field is in the clockwise direction. I can show that like that. I can show another magnetic field line over here. It's still clockwise, and so on. Okay, but I want it at a point here at point A, and I want it here at a point B. So how do I figure out the direction at this point? There's two ways to think about this. One is there will be a circle, if I draw it big enough, that'll go through this at point A. I'm just showing you a little arc of it. Okay, and at point A, I have to figure out a tangent line. So the tangent line to the circle will look like this. It'll go straight up and down. And because the direction of the magnetic field is clockwise, at this point, it's going to be following that clockwise pattern. And so it'll be going down and not up. So that'll be the direction of the magnetic field at point A. Similarly, at point B, you can draw a little arc. Again, the overall sense of this is clockwise, so it's going to be going this way. So at B, it's going directly to the left because the tangent line here is horizontal, and so it'll be going to the left, but it's a smaller magnitude as we saw before, so the arrow will be shorter. All right, that's one way to do it, is to imagine these bigger circles. Some of you find it easier to think about it in a different way, so I'm going to give you both the ways so you can decide which way you want to do it. The other way to think about it is when you have a point that you want the direction of the magnetic field to be determined, you can connect that point to the center of the wire with a straight line. Okay, and if this circle is fully drawn, you can see that the straight line that connects the point at which you want the magnetic field to the center of the wire is like the radius of that circle. And the tangent to the circle skims the circle and touches it at just one point. There is a rule in mathematics that says that the radius of a circle and the tangent of the circle at a point are always perpendicular to each other. So it'll be a 90-degree angle. So once you have the radius, you can draw another line that's perpendicular to it, and the tangent has to be along that line. Then all you got left is to figure out the direction. Is it going up or down? And because of the clockwise sense, in this case, it'll be going down. And in this case, the radius is going to be that line. So it's vertical, and the perpendicular to that would be a horizontal line. And so the magnetic field has to be horizontal, and then you know that it's got to go to the left because of the clockwise sense going through that point. Some of you will find this method particularly useful when you have a point that's not horizontal or vertical. So let's say there's a point over here for which I want to figure out the direction of the magnetic field. Once again, you can just connect that point to the center of the wire by a straight line that would form the radius. And then you want to find a line that's perpendicular to it. So in this case, it'll be like that, 90 degrees. And then because it's going clockwise, you'll know that it's going up and to the right like this rather than down. Just to review the other method, if you were to imagine an arc of a circle going through here, the tangent points in the same direction. So you've got two methods to choose from to determine the direction of magnetic field at a given point. So the important thing to remember here is that clockwise would be a correct answer if you are talking about magnetic field lines, which give you a general sense of what the magnetic field is in a region of space. But clockwise would not be the right answer for the vector at a point. In order to figure that out, you have to do what we just talked about, one of two ways to do it. And the way we did it is a clockwise curve going through A. At A, the tangent will be going down. So this will be BA. And then a clockwise through point B will be going to the left, horizontal, shorter length because it's a shorter magnitude. So this will be BB. So we have figured out the magnitudes of these magnetic fields. We have figured out the directions of these magnetic fields. So we have answered the questions we were asked. So we're done with this problem. All right, so in this video, we figured out how to determine the magnitude and direction of magnetic field from a long, straight current carrying wire. In the next video, we'll talk about determining the net magnetic field from two separate currents in two different wires.